Hello everyone. In our previous session, we have explored into the general characteristics of a workpiece which must be analyzed before initiating the manufacturing process. We have also discussed three fundamental aspects of a workpiece characteristics such as general description, shape and size of the workpiece, and material selection. Now we are ready to move to the next key considerations in the manufacturing planning, that is, originating operations, recorded changes in design, and resistance to the damage in processing in this session. Originating operation gives an understanding how a workpiece is initially manufactured, whether through a casting process or a forging process or a extrusion process, and how it influences the tolerances and machining strategies. Recorded changes in design ensures that the latest design revisions are accounted for the manufacturing process to avoid the errors and inefficiencies. And the third one, resistance to damage in processing, that evaluates how the material and geometry of a part affect its exposure to the deformation or defects during the manufacturing. Okay, let us move forward and discuss them one by one. First, let's take the originating operation. Before a part undergoes a detailed machining or further processing, it is first created through an originating operation, which is the fundamental process that gives the workpiece its initial form. The process could involve casting, forging, extrusion, rolling, or other primary manufacturing methods. Understanding how a part originates is essential because it is directly affects the dimensional accuracy, tolerances, and surface quality of the product. Unlike the material specifications and geometric details, the originating operation is not always explicitly mentioned on the technical drawing. However, it can often be inferred through a footnote, annotations, or general manufacturing knowledge. For instance, a note like cast pattern number here suggests that the workpiece is produced through the casting process. Similarly, when working with metallic components, recognizing whether a part is forged, cast, or extruded helps the engineers to determine the necessary machining allowances, potential defects, and process variations. Certain engineering drawings provide more explicit details by including multiple set of drawings, such as forging drawing and a machining drawing. The forging drawing shows the raw shape of the material before machining, while the machining drawing highlights the final dimensional specifications. By analyzing both, the engineers can predict how much material must be removed and which machining operations are required to achieve the final design. So, by understanding the originating operation, we can estimate the dimensional variations and setting appropriate machining tolerances. It allows the process engineers to anticipate the surface irregularities such as string gauge cavities in casting or scale in forging. It also influences the tool selection, cutting parameters, and process sequencing to ensure an efficient workflow. For example, consider a cast iron engine block. If the originating operation is casting, the process engineer must account for casting defects, string gauge allowances, and rough surface texture while planning the subsequent machining steps. On the other hand, if a component is forged, it will have superior strength and grain flow, requiring different machining techniques to accommodate its hardness. So, by identifying and understanding the originating operations, manufacturer can improve the process accuracy, reduce the waste, and optimize the production cost. This step ensures that each part is processed appropriately, maintaining the quality standard and dimensional accuracy. Next, we will move to the another one important aspect of workpiece characteristics, that is, recorded changes in design. Engineering drawing often undergo revisions for multiple reasons, such as correcting errors, reducing cost, improving the manufacturing efficiency, enhancing the inspection method, or evaluating overall product quality. Many of these revisions are initiated by the process engineers who identifies the area for improvement based on practical production challenges. However, failing to check for recorded design changes before the process planning can lead to costly manufacturing mistakes, affecting everything from the operation sequencing and tooling selection to location systems, auxiliary operations, and production cost. Since most components are part of large subassemblies or assembly, modifications in one part must cross-checked with related to drawing to ensure they do not create any misaligned interference or functional failure in the final product. Simply reviewing the changes at the individual part level is insufficient. Instead, the process engineer must assess how these revisions impact the overall systems and request clarifications from the product engineer if necessary. For instance, if an automobile manufacturer modifies the dimensions of a crankshaft, these changes must be reviewed in the relation to the bearing house alignment, piston clearance, and lubrication pathways to prevent the mechanical failures. Overlooking such dependencies could lead to significant performance issues, costly reworks, and production delays. By ensuring that all recorded design changes are thoroughly evaluated and properly integrated into the manufacturing plan, the process engineer enhance the product reliability, reduce the material wastage, and optimize the workflow efficiency. This proactive approach helps to prevent the last minute surprises on the production flow, leading to smoother manufacturing operations and better quality control. Now that we have understood the significance of recorded design changes, let's move to the another vital consideration in process planning, that is resistance to damage in processing, which determines how well a workpiece withstands the handling, machining, and other manufacturing stresses. We can say this in another way, that is the damage due to increased precision and reduced the material allowances. In these initial stages, the rough machining or forming operations may not pose a significant risk, but as finer tolerances and delicate features are introduced, the potential for damage is increased. Certain materials such as brittle ceramics, thin walled components, or heat treated metals require a special handling to prevent the cracking, deformation, or surface defects. Similarly, the components with intricate geometries, sharp edges, or thin sections can easily be compromised if it is subjected to improper clamping, excessive cutting forces, or inadequate support during the machining process. The process engineers must account for these weaknesses when designing the manufacturing workflows. This includes selecting the appropriate tooling, fixturing, and machining parameters to minimize the stress on the workpieces. For instance, reducing the cutting speeds, using a specialized cutting fluids, or employing the vibration damping setups can helps to prevent the unwanted damage. Additionally, intermediate heat treatment or stress relieving operations might be necessary to improve the material's workability and reduce the livelihood of the defects. Another key aspect of preventing the damage is proper material handling and storage throughout the production cycle. Certain components may require a protective coating, controlled environment, or cushioning method to avoid the scratches, corrosions, or deformations. For example, electronic control parts or a precision optical components must be handled in clean, static free environment to prevent the contaminations or electrical discharge damages. Large and heavy components such as engine blocks or aerospace structural elements require special lifting fixes or automated handling systems to prevent excessive stress and warping. Ultimately, understanding resistance to damage in processing is essential for maintaining the product integrity and reducing the costly reworks or scraps. By carefully analyzing the part print and material properties, process engineers can implement a preventive measure that safeguard the components throughout the manufacturing process. This ensures that parts meets the quality standards, functions as intended, and integrates seamlessly into the final assemblies. So, by understanding the general characteristics of the workpiece, including the description, configuration, and material selection, the process engineers can establish the foundation for a well structured manufacturing plan. Further, analyzing the originating operations helps to determine the initial form of workpiece and its impact on machining processes. Reviewing recorded design changes ensures that manufacturing aligns with the latest specifications, preventing costly errors and inefficiencies. Additionally, evaluating the resistance to the damage in processing allows the engineers to implement the necessary precautions to protect the delicate or precision components from deformation and defects. I hope now you have clearly understand the general characteristics of the workpiece. Thank you and happy learning.